Today in the workshop we'll be working with the MPU-6050, an Inertial Measurement Unit. We'll see how the MPU-6050 works and how to use it with an Arduino. We'll also build an electronic level. It's a well-balanced episode today, so welcome to the workshop. Hello and welcome to the workshop. Today we are going to be working with the MPU-6050, which is an IMU with 6 degrees of freedom. Now, if none of that makes any sense to you, don't worry. I will be explaining that in a few moments. But essentially, this is a device that contains both a gyroscope and an accelerometer, and it can be used to measure inertia, it can be used to measure position, rotation, etc. You'll find devices like this used in things like self-balancing robots and in robot arms. You'll also find it in quadcopters and other devices like that. You'll even find a device like this in a hard disk because it's used to sense whether the hard disk is being dropped toward the floor. Now, this is a very sensitive and very complex device, yet it is quite inexpensive. And this video, by the way, is something that many of you have requested that I do. And the way that this was requested was by using the form that I've provided for doing that, the survey form. And you will find a link to that survey form at the bottom of every one of my newsletters, as well as in the welcoming letter for the newsletter. So if you haven't signed up for the newsletter, please do so, especially if you want to suggest content for videos, because I'm not taking suggestions via email or via YouTube or website comments anymore, simply through the survey. The survey allows me to find out just how popular your suggestion is so that I know what videos I can make that you will appreciate the most. So back to the MPU-6050. What we're going to do today is we're going to learn a little bit about how it works and what some of these terms like IMU and degrees of freedom actually mean. And then we're going to do a little test of it using a library, or a couple of libraries actually, that you can download directly from the article that accompanies this video on the dronebotworkshop.com website. And then after that, we're going to build a little project, one that's going to replace one of the tools I have right behind me. This particular tool is the one we're going to replace. This, of course, you'll recognize as being a level. So we are going to build a digital level. So, as always, there is a lot to cover today, so let's learn a little bit about the MPU-6050. Let's take a look at the MPU-6050 IMU. The MPU-6050 is a low-cost and accurate IMU. An IMU is an Inertial Measurement Unit. The MPU-6050 consists of both an accelerometer and a gyroscope. Devices like this are used in UAVs like quadcopters and helicopters. IMUs are used in robotics applications such as positioning robot arms or keeping self-balanced robots balanced. They're also used in phones, games, and they are used in hard drives to lock the heads when they detect that the hard drive is being dropped. Now let's take a look at the accelerometer function. As the name would imply, an accelerometer is something that measures acceleration. Let's imagine a box that has 6 sides, like any box. We'll label the sides X plus, X minus, Z or Z plus, Z minus, Y minus, and we're looking down at the box right now from the Y plus. Now let's place our measurement device in the center of the box. Our measurement device will remain stationary, but the box is free to move. Right now everything is still, so the X, Y, and Z values are all zeros. Now we accelerate the box in the direction of the X plus. The acceleration is in that direction, while the inertial force is in the opposite direction. Now the X value will be 1, the Y value 0, and the Z value will be 0. Let's bring our box back to the stationary position, and X, Y, and Z are now all 0 again. Now we will accelerate downward. Our initial force again is in the opposite direction. Our X value is 0, Y value is 0, and the z value is -1 because we're going in the downward direction. Now let's accelerate in the direction of the x plus and the z minus. Our x value will now be 0.707, our y value will be 0, and the z value will be -0.707. A gyroscope is a device that can measure rotational movement on 3 different axes, the x, y, and z axis. The gyroscope used in the MPU-6050 is called a MEMS gyroscope. MEMS is an abbreviation for Micro-Electro-Mechanical System. Now, MEMS sensors produce a voltage when the respective axis is rotated. These voltages are sampled with a 16-bit analog-to-digital converter inside the MPU-6050. The MPU-6050 also has a temperature sensor. In addition, it has a digital motion processor, or DMP. This DMP correlates the data from the accelerometer and the gyroscope. You can also use external third-party sensors with the DMP, such as a magnetometer. These external sensors will connect using a second I2C bus. Now here's the MPU-6050 module that I'm using. Note that there are many different styles of module, but this is a very common one. The first pin is VCC, which for this module is 5 volts DC. Note that the MPU-6050 is actually a 3.3 volt device, but there's a voltage regulator and some resistors to do voltage level conversion on this module. The next pin is simply a ground pin. The SCL pin is the I2C clock pin, and the SDA pin is the I2C data pin. The XDA pin is the external I2C data pin. This is what would be used if you're connecting something like a magnetometer or other third-party sensor to the MPU-6050. XCL is the external I2C clock. The AD0 is an I2C address bit selector. You can use this to change the I2C address of the module. In actual fact, the module has 2 I2C addresses. The INT pin is an interrupt output pin. And the module also has markings to illustrate the X and Y orientation of the sensor. So now let's start working with the MPU-6050. So here's a look at the MPU-6050 module that I am using. Now, it's a rather tiny little device. This is a typical MPU-6050 module, although there are other ones as well. We'll just bring it so you can sort of see it. All the connections are up on one side over here, and the actual MPU-6050 is right here on the module itself, and there really isn't anything on the back of the module. So it's a very basic little module, has a couple of mounting holes in it, and as I showed you earlier, it's also got some markings here for the orientation so that you can tell which way the X and the Y axis are on the module. Now, in order to use this module, as you'll see in my demos, I'm going to actually mount it onto a small little wooden stick to make it a little easier to manipulate. But there you are, a tiny and inexpensive MPU-6050 module. Now, one of the specifications that I didn't cover in the presentation you just saw about the MPU-6050 is that it is advertised as having 6 degrees of freedom, which may be a bit confusing because most of us know what a degree of freedom is. They represent the ability to move in the 3 different dimensions, height, width, and depth. So how can this have 6 degrees of freedom? Well, the answer is it's the combination of the 3 degrees of freedom that the gyroscope has and the 3 degree of freedom that the accelerometer has. And you'll see other IMUs advertised as having 9 degrees of freedom, and those ones typically have, in addition to the gyroscope and accelerometer, they have a magnetometer in them as well, and that would provide an additional 3 degrees of freedom. So that's what the term 6 degrees of freedom means, just in case you're a bit confused about that. Now, on to our first experiment. What we're going to do is we're going to hook up the MPU-6050 to an Arduino, and we're going to use a couple of libraries first, which are quite complex, but they will show you how the device works, and indeed it'll show us how we can test the device. I'm going to mount my device on a small piece of wood in order to make it a little easier to manipulate. One thing that some of you who are very observant might realize when I start getting into the demos is that I normally work on a Linux machine, and today we're working with Windows, and you might wonder why that is. Well, we had a little bit of a crisis here in the workshop earlier this week. The SSD drive on the workshop computer, which is a Linux computer, just up and died, which was quite a surprise to me because the drive is only 4 months old. However, it is what it is. So I brought a Windows computer in order to be able to create the video on that. I do have a new hard drive SSD drive to replace the one that had died, and I will be getting that fixed up so Windows is only a temporary arrangement over here. And for any of you who might be concerned, no, I didn't lose any data. I don't keep my data on my computers. I keep it on a network storage device, which in turn is backed up to a cloud. So that was safe. It was just really an annoyance. So having explained the Windows saga to you, let's go and see how we can hook an MPU-6050 up to an Arduino. So here's how we'll hook up our first experiment. You're going to need an Arduino Uno and an MPU-6050 module. Now your module may be slightly different than mine, but it should have similar pinouts. We'll start by connecting the VCC on the module to the 5-volt output on the Arduino. We'll connect the module's ground to the Arduino's ground. The SCL, which is the I2C clock line, is connected to analog input A5 on the Arduino. Now some Arduinos also have an independent SCL and SDA input, and you can use those instead. In a similar fashion, the SDA on the module is connected to analog pin A4 or the dedicated SDA pin on your Arduino. And finally, the interrupt pin on the module is connected to digital I/O pin number 2 on the Arduino Uno. So now let's take a look at some code we can use to work with our MPU-6050. Now for our first test with the MPU-6050, we're going to use a couple of libraries that are provided by Jeff Roberg and that are up on GitHub. Now Jeff has written an entire set of libraries for developing with the I2C bus, and these libraries are not just for the Arduino, they're also for a number of different microcontroller units. Now, you may find it difficult to pick out the two libraries that we are going to need, and so what I've done is I've created zip files of them, and I've placed them on the article that accompanies this video on the dronebotworkshop.com website. And of course you'll find the link to that article right below the video. So download both of the zip files, and the next step will be to install them into your Arduino IDE. So go into the Arduino IDE and go up to Sketch, and go to Include Library, and go to Add Zip Library. Navigate to where you've placed your libraries. Mine are in my Downloads folder, and these are the two you want to install, I2C Dev and MPU-6050. Now you'll need to do this operation twice, once for each of the libraries. Once you've installed this into your Arduino IDE, which I won't do because I've already done it, you can now go and open the example files that come with it. So go into Examples and scroll down until Examples from Custom Libraries, and you'll see MPU-6050. Go into Examples, and we're going to look at this first one, MPU-6050 DMP6. This will be one that illustrates the use of the digital motion processor that is contained in the MPU-6050. Now this is a very extensive piece of code, and I'm certainly not going to go through it line by line. Quite frankly, I don't particularly understand all of it myself. However, there are a few facts that you should know about it, and some things that you may need to change to get your code working. Now at the beginning, of course, you can see it includes the two libraries we just downloaded, and also includes the built-in Arduino wire library for talking to I2C. Now, the default for this class is to use hexadecimal 68 as the address for the MPU-6050. Now, that is the default address that my module is using, so I don't need to change anything. However, you can use a statement over here and change it to a different address. If, for example, you've used that address 0 pin on the MPU-6050 to change your address, you may need to change the address over here. Another thing to note is down in the setup. And we'll get down to the setup over here, and we will look for the serial monitor. Now it is set to use a very high baud rate on the serial monitor. Now there are notes here about using Arduino Pro Minis at 3.3 volts and 8 megahertz and having to drop that. Also, for the demonstration we're using, you could change this if you wish, because this is really used for the teapot demo, which is an external demo that uses the processing program, and we aren't running that one today. You'll find several examples of that, by the way, up on YouTube. But I'm leaving this at the high baud rate, but just remember to change your serial monitor to that rate. Otherwise, as I said, this code is very well commented, and so you can go through the code to find out exactly what it does. It does a lot of things that are well beyond what most of us would have to do unless we're building things like quadcopters or something. For example, this one here, output readable quaternion. Well, what exactly does that mean? Well, I had to actually look that up myself. And in mathematics, quaternions are a number system that extends the complex numbers, first described by Irish mathematician William Rowan Hamilton in 1843 and applied to mechanics in three-dimensional space, which is quite something. Now, this outputs it in the easy matrix form of WXYZ. Well, what does that mean? Well, a quaternion with a complex number with a W, the W is the real part and the X, Y, and Z are imaginary parts. And I'm reading this, by the way. If a quaternion represents a rotation, then W equals cosine of theta over 2, where theta is the rotation angle around the axis of the quaternion. So this is pretty heavy-duty stuff and is not something we're going to go through today. What we are going to do actually is go down and get this output over here, and this is what our demo is going to give us, the yaw, pitch, and roll values. Those of you who work with quadcopters and other flying devices will be familiar with yaw, pitch, and roll, representing the different degrees of freedom that your quadcopter or other flying device can go in. So that's what we're going to be representing with this serial monitor today. But again, this code is very well commented, and so if you would like to do something very complex with the MPU-6050, this indeed is the code to use. So what I'm going to do right now is load this onto our Arduino with the MPU-6050 and do a quick demonstration with the serial monitor just to see the results we get for yaw, pitch, and roll. Okay, so I've got my demo over here. You can see my MPU-6050 mounted on its piece of wood, which I'm using just so that it's a little easier to see what direction I'm holding it in while I manipulate it. And we've got the serial monitor on, and it starts off saying initializing I2C devices, it's tested the connection, and it's connected successfully. Now what you need to do is you need to use the send line in the serial monitor to send any character you want in order to get this started. So I'm just going to send a character to it. It initializes, and we're getting yaw, pitch, and roll values. And so watch what happens as I move my sensor around. And as you can see, it is indeed manipulating those yaw, pitch, and roll values on the monitor. And so this pretty well proves out that our MPU-6050 is functioning correctly. So now let's move on and look at another sketch, this one that does not use these libraries. Alright, now we've seen how the MPU-6050 works with the two libraries, and as you can see, it is capable of giving back a wealth of information regarding the position of the device, the acceleration of the device, the movement of the device, etc. But for our next project, we don't need all of that information, so we aren't going to be using those libraries. Instead, we are going to work directly with the chip, just using the Arduino wire library. Now, our project is, as I said at the beginning of the video, a digital level, and this is actually a practical project. Now, I'm doing it on a breadboard, but you could easily put this into a case and use it as an actual tool. So you might want to take a look at building one of these in a permanent version, perhaps using something like an Arduino Nano or a Pro Mini instead of the Arduino Uno in order to reduce its size. But at any rate, what we're going to do right now is take a look at the hardware we're going to need to attach to the Arduino in addition to the MPU-6050, and then of course we will look at the sketch, and then finally do a demo of our digital level. Now, to build our electronic level, we'll require the following components: an Arduino Uno or another similar Arduino. If you want to make a smaller version of the level, you could use an Arduino Nano or a 16 MHz Arduino Pro Mini. We'll also, of course, need the MPU-6050 IMU and a liquid crystal display with an I2C connector. We'll also be using 5 LEDs. I used 2 red LEDs, 2 yellow LEDs, and a green LED, but of course you could substitute different colors or even use an LED bar graph assembly if you wish. And finally, we require dropping resistors for all of the LEDs. I'm using 5 220 ohm resistors, but any value from 150 to 470 ohms should work fine. We'll begin by connecting the 5-volt output of the Arduino to the VCC connection on both the MPU-6050 and the liquid crystal display. Next, we'll connect the ground to the ground connection on the MPU-6050 and the LCD display. We'll also connect the ground to the cathodes of all of our LEDs. Analog input A4 is also the SDA signal. Connect this to the SDA connection on both the MPU-6050 and on the LCD. Analog pin A5 is the SCL signal. Connect this to the SCL on the MPU-6050 and on the liquid crystal display. And finally, we need to connect the anodes of all of our LEDs to pin 9, 10, 11, 12, and 13. Each will run through a dropping resistor and then head to the respective LED. Now that you have it hooked up, let's take a look at the sketch we'll use to build our electronic level meter. Now, before you run the sketch, you're going to need to install yet another library into your Arduino IDE. Now, this is for the liquid crystal display using I2C, and it's the new liquid crystal library. You can get it on Bitbucket, and you'll find the link in the article associated with this video. Once you've downloaded the zip file, move into your Arduino IDE and install it in a similar fashion to how you installed the other 2 libraries in the sketch we looked at earlier. Now let's take a look at this sketch. We start off by including the wire library, which is the built-in library for working with I2C. Unlike the last sketch, we're going to work directly with the MPU-6050 through I2C. Then we also need to install the library that we just installed, the Liquid Crystal I2C library. We defined the connections to the LCD. These are actually the connections on the adapter on the LCD, the I2C adapter. And we need to define the address for the LCD. So if you have a different address, you'll need to change that. After that, we define the LEDs that we're going to be using for our bar graph display, and so we do that over here. Next, we set up a number of variables for our gyroscope, and these are all a number of different floats, longs, and booleans that we're going to be using to do the calculations in order to determine the pitch and the roll, which is what we're trying to do today. We also set up a couple of timers and a counter that we're going to use on our display. This is because we're going to be bringing the data back very fast, and we cannot display everything on the LCD display. It is simply too fast for it. Now in the setup, we'll start the I2C, and we'll set up the LCD as a 16 by 2 character LCD. We'll also define all of the LEDs as being outputs. Then we call a routine that I'll show you in a moment that set up MPU-6050 registers. This is the one that's manually going to go and do what we did with the library earlier. Now in this section over here, we actually need to read the gyro data and the accelerometer data 1,000 times, and this is in order to stabilize the device. So there's going to be a delay when we start off, and so you will expect when you first start this project that nothing will happen probably for close to 7 or 8 seconds. We divide all the results we've gotten by 1,000 in order to get the average. We'll start the serial monitor. Now I have this remarked out right now because the actual project doesn't use the serial monitor, but I've put it in there in case you need to do some troubleshooting. Note the speed of the serial monitor. It has to be that fast in order to display all the data. This is why we can't display it all in a liquid crystal at one shot. We also set a timer up, and we use the micro command. Now what that function does is it counts the number of microseconds since the Arduino has been powered up or rebooted. You might remember some of our other sketches used the millis command, which counted the milliseconds. This counts microseconds. Now before we look at the loop, let's quickly go down and take a look at the functions that we have at the bottom over here. One called setup MPU-6050 registers, and in this one we use the wire library to manually set a number of the registers for both the accelerometer and for the gyroscope. There's also one to read the MPU-6050 data, and this reads the raw data from the gyroscope and the accelerometer. And again, we are just simply doing this, well not simply, but we are doing this with the wire library directly on I2C. Now these statements over here you may have not seen before with what looks like 2 less than signs and an 8. What that actually does is it shifts things by 8 bits, and this allows us to take 2 8-bit values and turn it into one 16-bit value, which is what we'll need to do in order to read the data because it will not fit into an 8-bit value. Now let's go back up into our loop. Now there's a lot of mathematics over here, and we're not going to go right into that, but we'll start off by getting the data from the MPU-6050 using the function we saw before, and we'll calculate the offset for the gyro. After that, again, a number of calculations in order to do the roll and the yaw angle. Then the accelerometer calculations. Again, I'm not going to go over all the math over here, and many of these functions are in the public domain. I certainly didn't write these all myself. When we finally get to the bottom of this, we are going to take the average of everything, and what we are going to get is the pitch and the roll output, and that is what we're looking for. It's actually the pitch output that determines the level, but we're also going to display the roll on our display. Now, our display can only handle so much data, so what I've done is I've divided it and taken only every 100 counts. Now, you can play with this number if you want to make it more responsive, but if you go too low with this number, the display is not going to be able to keep up with the data. So we use a counter over here, and once it has gone over 100, we'll go and print on our display. So we first clear the liquid crystal, and then we go and print on the first row of the LCD. So we set the cursor position and we print pitch, and then we actually print the actual pitch. And then we move the cursor to the next row and we print roll and print the actual roll. And now we go into our LEDs, and the LEDs are looking at the pitch output, and it's looking at what range they are in and determining which LED should be turned on. So for example, if we want to go on to the level LED, the one that's in the middle, we'll go and look at this one over here. So if the pitch angle is within 1 degree of 0, then we'll turn on the middle LED to say everything is level. Now you can adjust this if you want to make this more fine-grained. You might make it only half a degree or something like that, and similar to all the other LEDs over here. Keep in mind, too, that you could also use a sketch like this in order to light an LED when something comes to a specific level. It doesn't actually have to be 0 like I'm using it over here, and you might have an application where you want to trigger something when the sensor is at a specific level, and you could use that. And so after that, we'll set the display count back to 0 and go out of there. And then we use a timer over here we've used with Micros in order to make a small delay. We reset the timer and we finish the loop and start it over again. And so there's a lot to this sketch. A lot of it is mathematics, but it's all very well commented over here if you want to read the sketch and understand what the math is actually doing. And so now that we have seen the sketch, let's load it up to our project and take a look at it in action. Alright, here's our demonstration all hooked up. I'm going to plug the power into it right now. And when you first start off, remember it has to calibrate itself, so you'll see nothing on the display at the beginning. And there we go, we have a display, and also our center LED is lit because everything's pretty flat. Now let me lift up the end a bit, and as we go up the yellow one, and the red one, and notice the pitch values there are negative. I'll bring it back down to the center and move it up over here, and they're positive. And of course, as we go above, it just stays with the red LED because we've exceeded 2 degrees. And move it back down into the center. You can also see the roll values when if I rotate it, you'll see that the roll values are changing as well. And so there you go. It seems to work very well, and you could actually use this as a permanent project if you wanted to put it into an enclosure and maybe use a smaller Arduino with it. And so our electronic level meter seems to work quite well. Okay, well this brings us to the conclusion of the video, and we've done quite a bit today. We've learned about the MPU-6050, and we've built a little electronic level, which can actually, as I said, become a practical project if you want to put it into a different case and maybe use a smaller Arduino with it. And I'd like to thank you for having joined me today. Now, if you need any of the code, or if you need the 2 libraries that I used in the initial demonstration, you will find those all on the article that accompanies this video, and that's on the dronebotworkshop.com website. There is a link to that article right below the video. And while you are on the website, please sign up for the newsletter if you have not already. Remember, this video was something that was suggested by my newsletter subscribers. And so if you'd like to suggest a video, you'll find a link in the sign-up letter, as well as the bottom of all of the newsletters going forward, that you can use to go to the survey, to input your suggestion, and also vote on some of the other suggestions for topics, for videos, and articles. And on the subject of subscribing, if you have not done so already, please subscribe to the YouTube channel. I would be very appreciative of that. So until next time, please take care of yourselves. I hope none of your SSD drives fail, and I hope to see you very, very soon here in the workshop. Goodbye for now.